So we finally come to the last video, and you're going to have to hold your crying until later on because we're going to learn about disaccharides and polysaccharides. Now, you may have heard the terms before, but we'll go over them briefly and then I'll kind of expand on some of these. A disaccharide, obviously, as the name hopefully implies, contains two sugar units. It has a formula that's different than a monosaccharide because essentially when two monosaccharides come together, they lose water to produce the disaccharide. So the formula is CnH2n minus 2 ON minus 1. There are three very common disaccharides that we encounter on a regular basis. The first one is sucrose. The second one is lactose, and the third one is maltose. And I'll talk a little bit about each one of these in just a little bit. The next subject is polysaccharide. So a polysaccharide, as the name implies, is a polymer of sugar units. And there are many polysaccharides, but there are two main types of polysaccharides. The first one is what we call amylose. Amylose is the major polysaccharide of starch. Starch contains, it's actually fairly complex branching of polymer units of sugars, but amylose is kind of a straight chain version of that. And so we'll talk about amylose in a little bit. And then the second one is what is referred to as cellulose. Cellulose is the major component of plants, and so in the world of nutrition, we call this fiber, right? So let's explore a little bit. We won't go into great detail about disaccharides and polysaccharides, but I do want you to know some of the nomenclature behind them, right? So let's start off with disaccharides. And I said that there are three main disaccharides, and we're going to talk about those three disaccharides and a little bit about their structure. So the first one is sucrose. Now, sucrose, you may know as table sugar. That's right. Glucose, which we always talk about glucose, is actually not table sugar. Sucrose is table sugar, and it is composed of glucose and fructose. So glucose and fructose make sucrose. Sucrose is table sugar. And so when we look at sucrose, we see, again, glucose and fructose make it up. And so in terms of the structure, we see that we have a glucose ring, and connected to that and notice this is alpha, the alpha anomer of glucose. So there is an alpha linkage, we call it, and that alpha linkage is connected to fructose. So here's fructose, and notice fructose, so the C1 carbon of glucose is connected to the C2 carbon of fructose, because remember the C1 carbon is that OH, then it goes C1, C2 is part of the ring, and then C3, C4, C5, and then C6 is coming up. So C2, 3, 4, and 5 are part of the ring of fructose, right? So we have what we call an alpha 1 to 2 or 1-2 linkage. This is very important in terms of biochemistry because we see that we can digest certain types of linkages between saccharides. One of them being an alpha. Well, the main one being an alpha linkage. So we have enzymes that can actually digest and cleave alpha linkages. The other thing to notice is that sucrose is actually connected via both hemiacetals of the anomeric carbons of glucose and of fructose. So that's kind of a cool little thing. The second disaccharide is lactose. Lactose is often referred to as milk sugar because it is the sugar that exists in milk. And this is, some people have a hard time digesting milk, and we're actually going to see why. Now, lactose is composed of a galactose sugar and a glucose. So there still exists glucose as one of the monosaccharides, but there's also galactose. And we're really going to kind of dissect lactose and actually see how you determine what the structure of lactose is. So its structure looks like this. It has a galactose ring. So this is galactose. Notice galactose is an epimer of glucose, where the C4 carbon is the only difference. So if you know the chair conformation of glucose, then you can easily recognize the chair conformation of galactose because glucose has that C4 carbon, the OH is in the equatorial, and galactose, the OH is in the axial position. Now, glucose, the anomeric carbon of glucose is connected to the anomeric carbon of galactose is connected to glucose through the beta anomer, and glucose is connected at the C4. So we call this a beta linkage because the beta anomer of galactose is the one that is forming the ether linkage to C4. So we call this a beta 1 to 4 linkage. So a beta 1 to 4 linkage, or beta 1,4 linkage, it's often referred to as, right? So now notice this is a beta linkage, not an alpha linkage. Sucrose has an alpha, lactose has a beta linkage. We can easily digest sucrose. Some of us have a difficult time digesting lactose, and we're going to see why that is a little bit later on. Okay, so the third disaccharide is maltose. This is referred to as malt sugar, and it's essentially two glucose units that are linked through an alpha 1,4 linkage. So lactose has a beta 1,4 linkage, maltose has an alpha 1,4 linkage. But of course it exists as there's simply two glucose sugars that are connected to one another. And maltose is, so we get the name from malt, right? It is the main sugar of malt. It's also the main sugar of a lot of carbohydrates. And when we digest carbohydrates, complex carbohydrates, oftentimes we digest them down to maltose. So maltose is kind of that sweet, it's a sweet taste, just like sucrose is sweet. Maltose is also sweet. Maltose also has an isomer of it, and we'll talk a little bit about that. I'm not going to show you the structure, but so if you think about the structure of maltose, it's an alpha linkage, so I'm using the alpha anomer, 1,4 linkage, so it's connected to the 4 carbon of another glucose. And so there's, you see it's on the 4 carbon of that glucose, and so this is the structure of maltose. So whenever, if you understand that nomenclature, alpha 1,4, beta 1,4, alpha 1,6, then you can actually figure out the connectivity between two monosaccharides to make a disaccharide. So remember I said there's an isomer of maltose. It's actually called isomaltose. It has an alpha 1,6 linkage. So the alpha anomer of glucose is connected to the C6 oxygen on the second glucose monosaccharide, right? And so that's kind of how that works. Now, one thing that you might want to be asking yourself is, well, how do we actually know the composition of disaccharides? there's lots of questions that you can ask yourself. How do you know what the two sugars are? How do you know which one is connected to what and in what order? And all sorts of things that we can start thinking of. How do you know it's an alpha linkage versus a beta linkage? So the first thing that we can do is relatively easy, and that simply involves hydrolysis, because hydrolysis basically gives us our base units, what monosaccharides are actually connected together. Now, why is this? If we try to hydrolyze a disaccharide and nothing happens, then we know that there is an ether connection between carbons that are not part of the anomeric carbon, right? Because we know that ether bonds are relatively strong bonds unless they are a part of an acetal, right? So hydrolysis tells us that at least one of the sugars is connected via an acetal. If hydrolysis occurs, then we know that at least one of the carbons is connected via the acetal. Why? Well, recall when we were looking at pentamethyl ethers, when I put these in water in acidic conditions, what happened? I hydrolyzed the anomeric carbon, but all of the other ether linkages remained intact. So if I think about a sugar, if that sugar, a disaccharide, if the two sugars, right, one saccharide connected to the other saccharide, is connected via the anomeric carbon, the hemiacetal carbon, that is really the only way that I can get hydrolysis to occur. And so I'd get a free sugar over here, and then it would also lead to the other free sugar. And so this is exactly what happens. For almost all sugars, we see that the connectivity is through at least one of the anomeric carbons. And when we're talking about glucose, we're talking about the C1 anomeric carbon, right? Be it an alpha linkage or a beta linkage, it doesn't really matter. So that's the first step, and that tells us that one of the linkages is through the anomeric carbon. But what other questions, might we have? Well, basically, there's still three main questions that we have to try to answer. The first one, which carbon is the one attached at the anomeric carbon, or I should say sugar, right? Which carbon of which sugar is the one attached at the anomeric carbon? So for example, if I have a sugar that I know hydrolyzes into galactose and glucose, well, how do I know that the galactose anomeric carbon is connected to the glucose or vice versa, right? The other question that I have is, well, which OH group of the other sugar is attached? Is it also attached through an anomeric carbon? Is it attached through the C2 carbon OH or the C3 or C4 or C6? And then, of course, the third question is, what type of linkage? Since I know that I have an anomeric carbon, I can think about an alpha or beta anomer, and so I can have an alpha linkage or a beta linkage. So how do you evaluate this? Well, I'm going to kind of walk you through this using lactose as our example. So first and foremost, when I take lactose and I hydrolyze lactose, I get D-galactose and I also get D-glucose. So I can isolate those two, and so I know that there's D-galactose and there's D-glucose that make up the disaccharide of lactose. Now, keep in mind, D-galactose only differs from D-glucose in that C4 carbon, right? So they are epimers of one another, and it kind of makes it a little bit easy. Sometimes that can make it a little bit difficult in terms of spectroscopy, but at least, structurally we can recognize the two differences. So, well, what can we do with this? Well, we know that lactose can actually be oxidized with the bromine water into a carboxylic acid. Well, what part of the disaccharide can actually be oxidized? Only the aldehydic or hemiacetal carbon can actually be oxidized. So we know that one of the sugar units, be it galactose or glucose, has its anomeric carbon still intact, right? Because its anomeric carbon is going to be a hemiacetal. That hemiacetal exists in equilibrium with its aldehyde. And then it's that aldehyde that can be oxidized. So this is what we know so far. We know that one of the sugars has a hemiacetal. That's what we know. Why? Because it can be oxidized by the bromine and water. So what can we do? Well, we take what we know, and so far all we know is that we have a glucose and a galactose. So notice I'm drawing a structure of an epimer, right, where C1 is either alpha or beta, don't know what it is, so it's a squiggly line. C4 is also a squiggly line because I don't know if it's equatorial or axial, right? I don't know if it's glucose, equatorial, or galactose, axial. So that's C4. Notice the squiggly line. Now, it's connected to the other sugar, and of course, the other sugar is the other one, but again, I don't know the C4 squiggly line, and I don't really know where it's attached. So C2, C3, C4, or C6, any of those oxygens could be attached to the anomeric carbon. But what I do know is that there is a hemiacetal there. And that's the key, is that the hemiacetal has to exist because it's in equilibrium with its open form of aldehyde. And so we can draw that, opening up that ring to give us the aldehyde. So that's all I've done here. I'm simply drawing now the open form of lactose in whatever possibility it has. And so now when I oxidize that with bromine, I get I get a carboxylic acid there, right? And again, I'm not quite sure what that squiggly line is, and I don't know where the connection is. So actually all the C2, C3, C4, and C6, they're oxygens. I don't know if they're OHs yet, right? But now if I hydrolyze that bond, right, I'm going to get my my two units apart, and I can figure out what the two units are, and that's going to tell me which one of them is the free hemiacetal. And so when I do that and I analyze what I get the pyranose of D-galactose, right? So D-galactopyranose, which means that it's the one that has to be connected through the anomeric carbon. Because the other one that has the free hemiacetal available that can go back into its aldehydic form, right? It is the one that's being oxidized, and I get this, right? So this is, if you remember, gluconic acid. So I get D-gluconic acid. So D-gluconic acid tells me that that the glucose is actually the structure on the right and galactose is the structure on the left. So now I know that galactose is on the left, glucose is on the right. Galactose is the one that is connected via its anomeric carbon to glucose. But I still don't really know where on glucose we are actually connecting. So the next question is, which OH group is actually linking from glucose, right? What do I know? I now know that galactose is here, and it's connected to glucose, but it's connected via either C2, C3, C4, or C6. So what am I going to do? Well, I'm going to methylate everything, right? So I'm going to react this with methyl bromide in excess using silver oxide as my base. And what do I get? All of the OH groups on galactose get methylated. And now what happens to glucose? Well, the anomeric oxygen gets methylated. And now what do I know? I know that all of the others, except for the one that's making that linkage, that ether linkage, is going to be methylated. So, but I'm not sure which one that's going to be. But that's okay, right? Because I can find out. How can I find out? Well, I can hydrolyze again this methylated product of lactose, and what's going to happen? Well, the free OHs we see are going to be methylated, and the OH that's bound to galactose via that hemiacetal of galactose can be hydrolyzed. So that hemiacetal OR bond can be hydrolyzed, and it's going to give me an OH group on there. And so we can hydrolyze it. And that's exactly what we're going to do. We're going to react this with water with a catalytic amount of HCl, for example, and I'm going to get the galactose with the OH group on it, right? And what happens with the glucose? Well, I see that again that OCH3 gets hydrolyzed because it's I'm in aqueous acidic conditions. So it goes back to the OH, which makes sense to us. It's a hemiacetal. Now C2 stays in OCH3, so I know it's not connected via C2. C3 stays a methyl ether, so it's not connected. What happens to C4? There's an OH there. And so I know that C4 has to be the one that is actually connected. And sure enough, C6 is methylated as well. And so the key is that C4, the OH of C4, is actually attached to the anomeric carbon of galactose. So now I can start putting it together, and I see galactose is connected to C4 of glucose. So this is C1, C4 connectivity. But the question still remains, what is the linkage? Is it an alpha C1 to C4, or is it a beta C1 to C4? In order to figure this out, we have to go to biochemistry and turn to enzymes. Enzymes are very specific and selective in terms of what type of glycosidic bond they can actually cleave, right? Because remember, this is a glycosidic bond. And we have two main types of enzymes that cleave these glycosidic bonds. The first is lactase. Lactase cleaves beta glycosidic bonds. And then we have amylase. Amylase cleaves alpha glycosidic bonds, right? So lactase is beta glycosidic bonds, and amylase cleaves alpha glycosidic bonds. And when we put lactose in with either one of them, we see that the only enzyme that cleaves lactose is lactase. And notice, obviously, lactase was named as an enzyme that can break down lactose, milk sugar. And this is why we, as humans, sometimes develop what we call a lactose intolerance, because lactase is actually an enzyme that is produced in us when we are tiny little babies so that we can actually, our mothers can nurse us. But as we get older, our bodies produce less and less of it. And some of us, our bodies produce such small amounts that we actually cannot digest the lactose that is in milk, and therefore we develop an intolerance to it. And so that's basically what is happening there, that that lactase, we don't have enough lactase in our bodies to hydrolyze lactose. Okay, so now we know the complete structure of the disaccharide lactose. We know it has galactose and glucose. We know it's connected via the C1 bond of galactose to the C4 bond of glucose, and that it is a beta glycosidic bond. So we call this a beta 1,4 linkage. And we see that that lactase is the one that cleaves it. So that's kind of a cool little story to see how things, how our bodies and how enzymes work in terms of recognizing certain carbohydrates. And we can actually expand this idea to that of polysaccharides. So polysaccharides are simply polymers of sugars, and we're simply going to look at two of them, right? Cellulose and amylose. So cellulose is a polymer of glucose. So notice I am showing 3 glucose units, and notice the linkage between the glucose units. You should be able to, I hope, recognize what kind of linkage it is. So take a minute and try to think about what kind of linkage that is. And if you said it is a beta 1,4 linkage, you are correct, right? So this is a beta linkage. Now, remember, with lactose, lactose had a beta linkage. And we have a difficult time digesting lactose sometimes. And sure enough, with cellulose, we have a difficult time digesting cellulose. Now, because it is a polymer, and because it's so big, basically it simply doesn't absorb in our bodies. Unlike lactose, lactose is still relatively small, so it can cause irritations in our stomach. Cellulose is a big polymer, and therefore it just kind of works its way through our digestive system, and actually can kind of help in that cleansing process. And so that's why we call this fiber, right? And we certainly need a certain amount of fiber in our diets to keep us regular, right? And that's basically how it's functioning. It doesn't absorb into our digestive tract. The second type of polysaccharide, though, is called amylose. Amylose is the major component in starch, right? So both cellulose and amylose are polyglucose structures. But the only difference is that amylose is a polymer of glucose connected via, again, so notice, and I could obviously extend this chain further and further, but the main difference is that the connection is via an alpha, right? So it's an alpha 1,4 linkage. So alpha linkages can easily be hydrolyzed by that amylase enzyme. So notice the amylase and amylose polysaccharides and amylase enzyme. So we see that the alpha linkage is digested by amylase. And where do you find amylase, do you think? Well, actually amylase is in our guts, but amylase is also found in our saliva. And as a matter of fact, when we're chewing food that is starchy, if you chew your food long enough, you'll notice it starts to get sweet. And the reason for that is because the amylase in your sugar, in your saliva, is breaking down the starches, right, the amylose polysaccharides, into maltoses, right? So you get these little maltose and glucose sugars. And the maltose, if you recall, is two glucose. It's a disaccharide of two glucoses, and it has a very sweet taste to it. And therefore, that starchiness becomes sweet as our amylase starts to break down amylose into maltose. And where do you find maltose? Well, you can find, or where do you find amylose? Well, pretty much any time you can find a starch. So corn, potatoes, rice, pasta, all of these are high in starches or complex carbohydrates. And so that wraps up our discussion on disaccharides and polysaccharides.